Hello, scholars. Welcome to day one of our learning remotely. We're going to start a new chapter. Chapter 10 is on probability. So how likely is something to happen? Can we put a number value on how likely something is to happen? Our goal here, we're going to learn everything we can about probability in chapter 10. Chapter 11 is about statistics and data analysis, with the idea that when we've studied both, we can make predictions, use data to make predictions about how likely something is to happen. So I want to start today, this is on page 535, with a little reminder about how to make a histogram. So if we started with this table of values, let's see how this works. There we go. So the ages of people at a gym. So at the time this data was taken, there were 7 people at the gym who were between 10 and 19 years old. There were 12 people at the gym who were between 20 and 29. There were no people between 50 and 59. So you can kind of understand how what this table means. How can we turn that into a graph that helps us see visually what kinds of ages are people at this gym? That's one of our biggest jobs in these 2 new chapters, probability and statistics. Can you take information and present it visually? Because I could read that table to you, or I could show you that table, but it's probably much easier to understand what's going on at this gym if you see a picture. So how can I translate a table into a picture? So a histogram is one special kind of statistical diagram. We would take these ages, and we call them buckets or categories. So we're going to make one column in our graph for the people from ages 10 to 19. We're going to group together the people from 20 to 29 in their own column, the people in their 30s in a third column. So this is the goal here. You can see your textbook has made a picture for you. So I want to show you how you would arrive at this picture. So I start off by labeling my axes. My y-axis is going to be the frequency at which people in that category show up at the gym, and along the x-axis I have equally spaced buckets, is what we call them. So that first one is for people from 10 to 19, the second is for people from 20 to 29, and what I want to do is I'm going to label my vertical axis so that I have to give as few as 0 and as many as 12. So I might go 2, 4, 6, 8, 10, 12. And this is ages of people at the gym. Might be a title for my graph. Ages of people at the gym. So I'm going to look up, and I find that for 10 to 19-year-olds, there are 7 people. So 2, 4, 6. I'm going to make another color here. So I make a bar that's 7 spaces high. For people from 20 to 29, there are 12 of them. So 2, 4, 6, 8, 10, 12. So I make this bar 12 spaces high. These 2 bars should bump up right next to each other. From 30 to 39, there are 6 people. So that bar is this tall. From 40 to 49, there are 4 people, so 2, 4. Nobody from 50 to 59, and then 3 people in their 60s, so that's halfway between here. And whether you color these bars in or not is not a big deal, but you can see obviously that the textbook gets to make a much neater picture with colored in bars, but I want you to see sort of that process of getting it onto the page. And I'm going to ask you to do question 4 right underneath this on page 535 as part of your assignment tonight. So can you take information from a table like that, we call it a frequency table, and turn it into a histogram? So the next thing I want to talk about is sort of making the transition from what we know about likelihoods of things to happen. So is it likely to rain today? It's very likely. It's raining right now. But if you want to measure the likelihood, that measurement, the actual number that we put on that, is called a probability. So you have some experience already with using likelihood and probability in regular language. But just notice that we want to start to translate this idea into numbers. Something that is impossible, if it cannot happen, it has a probability of 0. And something that is totally certain to happen, is a 100% chance of it happening, has a probability of 1. So you can read here to just kind of start to make that transition between what you already know about likelihood to percentage chance of something happening and like an actual number probability of it happening. We can kind of walk through here. So just to practice, if we have a meteoroid and it has a probability of impact on the Earth of 0.75, what does that mean for us? Is it likely to happen? Is 0.75 high? Is it low? So starting to translate that, and you can kind of see here. Something with a 0.75 probability has a 75% chance of happening. It's likely to happen. It's not guaranteed, but it would be wrong to call it unlikely. It's likely to happen. So you can kind of practice those. There's 2 more examples right there. And then at the bottom of the page, I would like for you to answer number. I do that on the Promethean board too, huh? Would you answer numbers 1 and 2 and 3 here? So the rest of my goals for today, I want to talk about some key vocabulary for talking about probability and a notation for probability, and then how to actually describe some probabilities in a very mathematical sense. So an experiment, we're going to start off, I'm here on page 538. So an experiment is something that happens where you don't know the outcome before it happens. So it's really different from what we talked about. We spent a lot of time talking about functions. A function, you put in an input, maybe a bunch of things happen, but only one answer is going to come out at the end. And you, especially if you've plugged in that number before, you know exactly what's going to come out. When we talk about probability, there's something that has either some randomness or some unpredictability to it. So flipping a coin, we don't know, is it going to come out heads or tails? Rolling a die, we don't know, what's it going to come out? So these are experiments if we're talking about vocabulary that we're going to use. The ways that things could happen, the possibilities, are called the outcomes. A list of all the possibilities is called a sample space. And an event is just like one thing that happens. So you flip a coin and get a heads, or you roll a die and get a 6. That's an example of an event. The rolling the die is the experiment. The possible outcomes are 1, 2, 3, 4, 5, and 6. Rolling a 6 is a specific event. And then a sample space is just a list of all the events. So you can see some ways here that they've shown you how to say what the sample space is. So if I asked you what the sample space is for flipping a coin, you might say, we sometimes put them in curly braces, heads and tails, and we would just agree that you're going to use H for heads and T for tails. Or you could write out the word heads and tails. If I asked you for the sample space of spinning a spinner that's numbered 1 through 10, it would be the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here in example 1, they have a slightly more complicated experiment. This experiment has 2 parts. You're going to flip a coin and roll a die. So that means there's going to be a very much increased size sample space, because there's heads and there's tails, but each of those would have to get matched up with all the possibilities for rolling the die. So here, if you wanted to, you could say that this is the sample space. Heads with 1, tails with 1, heads with 2, tails with 2. Or if you were called upon to list it out, which you really might be, and your beginning foray into probability, you might have to write out a sample space. You could pick some appropriate sort of abbreviation, use H for heads and T for tails, and you might write this as your sample space. So as we get into the end of example 1, I want to bring up the idea of the fundamental counting principle. So if there are two possible outcomes when you flip a coin, and 6 possible outcomes when you roll a die, then there are 2 times 6, there are 12 possible outcomes for those 2 experiments together. It's called the fundamental counting principle. You take the number of outcomes for one experiment and multiply it with the number of outcomes for the other experiment. The fundamental counting principle. So I'm looking here at this monitoring progress question. How many outcomes are there in the sample space? And then list the possible outcomes. So if you flip 2 coins, I flip one coin, there's 2 ways that could come out. I flip another coin, there's 2 ways that could come out. So there are 2 times 2, 4 possible outcomes for that experiment. If I was going to write out the sample space, I might write something like, I could get heads with heads, heads then tails, I could get tails then heads, I could get tails and then tails. So 4 possible outcomes with those different combinations. All right, so one last idea is the idea of theoretical probability. The theoretical probability of something happening. What would the odds you would give yourself if you had to guess? Are the number of favorable outcomes divided by the total number of outcomes. So if you were saying, what's the probability that I roll a die and I roll a 1? Well, the only possible outcome that meets the criteria of this event is rolling 1, and there's one way to roll a 1, and there are 6 possible outcomes when you roll a die. So if I said event B was like roll a die and roll a 1. Here's my notation. I say the probability of event B, so it's a capital P, and then in parentheses, the name of the event we're talking about is a little, that's good. Perfect. The probability of event B. It looks a little like function notation. It's not the same as function notation. But nor does it mean to multiply. This is a special probability notation. We would say the probability of event B is the one way you could roll a 1 divided by the 6 different ways you could have a die roll come out. To finish up, I want to walk through example 2. As you are starting your study of probability, you will find that there are some experiments, you won't really have an idea right away of how many possible good outcomes there are, how many different ways there are to get that good outcome. So writing them all out is appropriate at the beginning. We're going to get more and more used to little experiments like this, and you might find that eventually you don't have to write them out. But for this question, if you, not you, but somebody were taking a quiz and had to randomly guess the answers to 4 true-false questions, what's the probability they get exactly 2 right? Well, you might have to write out all the different ways you could answer 4 true-false questions correctly and incorrectly. So that's what's done in this table here. To get 0 correct, you'd have to guess incorrect, 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 incorrect. That's what these 4 I's are. And if you're going to only guess 1 correct, that could be correct, followed by 3 incorrects, 1 incorrect, a correct, and then 2 incorrects. So 4 different ways to have exactly 1 correct. This is the row that's going to be critical for us. So we need to know how many different ways there are to get 2 correct. So that's 1, 2, 3, 4, 5, 6 different ways to get 2 correct answers of the 4 multiple choice. And the probability of getting exactly 2 correct when you're guessing at random is that 6 divided by however many possible ways there are to answer 4 multiple choice questions. So that would be taking all these answer choices that you wrote out. So 1 in the first column, plus 4 here, plus 6 here. Oh, wait a minute. Did you guys see that? So the 6 we have, notice there's 1 in this row, 4, 6, 4, 1. seen those numbers before? Like in the triangle? Those are the handshake numbers. That fourth row in Pascal's triangle. So that's 16 altogether. The probability of it guessing exactly 2 correctly is going to be 6 out of 16, which you could reduce to 3 out of 8. So big idea for today, if you want theoretical probability, you find all the number of possible ways to get the outcome you want and divide that by the total number of possible outcomes. So page 535, you're going to do question, is it 4, the one with the histogram? Yep. Page 536, you're going to do questions 1, 2, and 3, trying to decide if something is likely, unlikely, very likely. And then on page 542, so it's the end of 10-1. Page 542, you're going to work on questions 1, 3, 5, and 7. Oh, wait, I think I even... Yeah, so you can probably see that here. Questions 1 and 3 and 5. And I'm going to scroll it up a second. Just in case you're stuck without your textbook, you can zoom in on the screen and see these guys. So good luck. If you have any questions, if you have friends who have any questions, don't hesitate to reach out. Hope you guys are all well. See you tomorrow.